Okay, so today I want to talk about how understanding the shape of data can help you accelerate your data exploration, data analysis, and inform things like machine learning algorithms and everything. And I sort of had the pleasure of the mathematics behind this is relatively new. In mathematics, normally a branch of mathematics is hundreds of years old, sometimes even 1,000 years old. This is ones of years old. And I was in the room. It was my office mate in graduate school who he and his father, who's also a mathematician, invented this branch of mathematics. I remember them telling me, or him telling me about it and me saying, oh, that sounds stupid. And this is before big data was a thing. And he was telling me about how he could understand shapes of data. And I was like, oh, that sounds, quaint. And now I've realized the power of it. So that's what I want to talk about. So what do we think of when we hear the word data? Do we think of sort of masses of records, or like arrays of binary digits, or solutions to differential equations, or something close to Brandwatch's heart, mentions on social media, or if you're Uber, you might be interested in tracking every car in the world, all over the place, or possibly just every IP request worldwide as you go through the day, or the internet traffic from America to Europe, for instance, in this case, or financial data, for instance. These are all different kinds of data, and in this day and age, we're completely inundated with vast amounts of different types of data: structured data, unstructured data, text, financial, etc. And the question is, how do we? The buzzword around this is big data, and I would argue that big is not the correct term. That's sort of the marketing hype. And the question we want to really handle is, how do we handle these different and diverse big data sets? And again, big is not the issue here. I think big is becoming easier and easier. We're finding storage, parallelism, distributed computing. We can handle big. The real issue is that it's complexity. It's the complexity of data. And data can be small and complex. It doesn't have to be big and complex. Data can be big and simple, right? If it's 1 billion data points all along a line, that's a very simple data set to understand. But it could be very small data set. For instance, like cancer data is 10,000 dimensional gene expressions, but you might only have 700 patients. So it's 700 points, and you need to understand how, these points. That's a very small data set, but it's incredibly complicated. So for those that haven't seen it before, this is Conway's Game of Life, which is an algorithmic sort of cellular automata, which is based on very simple rules, but generates really complex behavior. So again, it's not about bigness, it's about complexity is the real, I think, the fundamental challenge going forward. And I think complexity of data is at least as difficult a hurdle as the size of the data. And complexity has many forms. It can be the structure. Here at Brandwatch, we do a lot of unstructured data, and understanding that has its own complexity. The format of the data could be geodata, it could be text, it could be financial, etc. These each have their own little complexities that you need to understand. And as I just mentioned, even small data sets can have quite sophisticated complexity. So what we would like is some way, when we are presented with a complex data set, is some sort of automatic organization of that data, right? Some sort of unsupervised way where the data kind of combines in collections, which we can sort of literally visibly understand, rather than just looking at 10,000 dimensional arrays of numbers, right? That's not very informative. So the paradigm that is put forward by this branch of mathematics is that any data worth its weight in salt has shape, and that shape contains meaning. And so if you can understand the shape, you can derive some meaning from that shape. But you already knew this. I guarantee everyone in this room has seen a picture like this, right? Where you have some data points and you find the line of best fit. And understanding that line is important, right? We're saying here that the data presented is approximated by a shape. That shape is a line. And understanding that line allows us to make predictions on future data points. It tells us the line actually enforces a relationship between the variables involved in the data. And then that relationship between those variables tell us exactly when we change one variable, how all the other variables will change. So it gives us drivers and understanding. But of course, not all data can be fit by a line. So classically, I challenge you to find a line that describes this data set here. So this is the sort of a classic situation of cluster analysis. But again, there is a shape here. The shape in this instance is 3 points, 3 isolated points. The centroids, if you want, or the meteoroids. But you can see there are definitely 3 distinct groups here. And understanding that, knowing that there are 3 distinct groups, allows you to make predictions. When a new data point falls in, you can say which one of the 3 are you a part of. So the points actually enforce a categorization on the data. So if we understand that this data set, whatever it is, there's 3 clusters, then all we have to ask is, which cluster are you? Now the problem is, already, cluster analysis and linear regression, which is the previous slide, are completely distinct branches of statistics. Completely different tools, completely different methodologies. And so you start to think, well, if I want to understand all the possible shapes of all the data, do I have to invent a whole new branch of mathematics each time I come up with a new shape? Because that's a bit disheartening. So you could ask, well, hopefully, maybe we've found them all. Maybe these are the only 2. Maybe there's just lines and clusters and that's it. And then of course someone comes to you and says, well, what about this? This is not a line. I can't fit a line to this. It's not a cluster because there's nothing in the middle, right? So should we now go about developing a branch of mathematics that's just good at loops and circles and how that's approximated? We could. And we could start to say, so you could ask, well, where do these kind of data sets arise? And they naturally arise quite often in any kind of data set which has recurrent or periodic behavior, right? You'll naturally see loops developing in that. And so, you know, if you know your mathematics, you'll say, periodic behavior, that sounds familiar. I might try to start to investigate this with Fourier series or Fourier analysis. That's what they do with periodic stuff. And you could probably come up with a decent theory that gets really, that gets loops. And then someone says, well, what about this? And you're like, okay, that's not a loop. It's not quite a cluster. It's got these sort of arms and leg, right? It's not a line. So now do I need a Y detector? Do I need to look for the mathematical theory of Y, right? And then of course I could just add another leg here, and now you're like, okay, well, so this could go on, and we're still only in 2D, right? There's many more phenomena as you go up. There could be voids or etc. So we want to not go down that path because that seems like a lot of work, inventing a whole new branch of mathematics for each individual shape as we go along. So the question is there a better way to model this data, or model data in general? Is there a way we could simply study all possible shapes simultaneously? And fortunately, there is a mathematics of shapes. Geometry is the one that jumps to mind, but it's about rigid shapes. There's another branch of mathematics, which is topology, which literally is derived from the word, it's the classic Greek word for place, but that's also what they use for the word space. So topology can literally be broken down as the study of space, the study of spaces, the study of all possible spaces. So topology in general is a study of sort of continuous surfaces and exotic shapes that are continuous and somehow connected. So topology is the mathematical formalism for measuring and representing these kind of continuous shapes. And it started in the sort of mid 1700s, and it's been up until about 10 years ago, a branch of pure mathematics. It almost had no application. And it wasn't until my office mate and his father found a way that they could port this kind of same study of the classification of all possible shapes to discrete point cloud, like data point clouds like the ones we were looking at earlier, which is distinct from this kind of thing, which is a very smooth, continuous, infinite object. So topology in particular studies the three C's of topology are continuity. Everything should be nice and continuous. It's very much about connectedness. How many pieces are there of the thing I'm looking at? Here there is one piece. And the last one is compactness, is that it should fit in a ball, right? Is essentially what compactness is. I should be able to find a ball that surrounds it. So I mean, you can study non-compact stuff, but it gets hairy. So non-compact stuff is things like singularities, where you get some point that just, like if I pinched this and pulled it off forever, right? So it just had this weird long spike that would not fit in a ball, right? So these are the kinds of things topology studies. In particular, it doesn't study point clouds. It doesn't study data sets. It studies continuous, flowing surfaces. And the three main features of topology, which are really sort of important, and when you see them, you realize that's kind of what you want for data analysis, is the first is coordinate free. In topology, these are all the same object. You don't care about the X, Y position. You don't care about coordinates. You just care about the shape. And they are basically the same shape. You also care about, you don't care about deformations. So these, and this is a bit of a lie, but in general, you're allowed to stretch and deform. It's kind of considered like Play-Doh geometry, right? If you can, without tearing or poking a hole, if you can malform things in any particular way, it's considered this very same thing. And humans are very good at this. We are very good at deformation invariance things. This is why different fonts don't freak us out, right? We can look at these and say these are all A's, because we're very good at recognizing deformation invariance, right? We can look at these and say, yeah, they're basically A's. Computers, on the other hand, are pretty crap at this, right? They're not so good at deformation invariance. And then the last one is topology seeks to find compressed representations of objects. So here we have an infinite sphere. There's an infinite amount of information, right? There's an infinitude of points on that sphere. But if I replace that sphere with an icosahedron, then it's just a bunch of vertices, some edges, and some faces. It's a finite object. I could study that thing, and for the most part, it's kind of that thing, especially if I don't care about deformations. In the eyes of topology, these are the same object. So why not study the one I can actually put into a computer rather than the one that has no hope of being represented on a computer, right? So topology seeks these compressed representations in order to sort of make sense of shape. So where did topology start? As I said, it started in the 1700s. The Swiss mathematician Leonhard Euler was challenged by the King of Prussia. He was given the 7 bridges problem of Königsberg, which asks, I don't know if you can see it, there are 7 bridges highlighted there on this very archaic map of Königsberg. And the question was, is it possible to start anywhere you like? Can you cross each bridge once and only once? And so Euler's solution was, there's a lot of data here, right? Is it really significant that there are buildings and other streets? Probably not, right? That's not going to help my bridge crossing question. So immediately you could probably eliminate a lot of that data and go down to this sort of somewhat compressed representation of just the bridges, just the land masses. And then he went even further and said, well, I could just write that like that, because again, I don't care if I'm allowed to deform things. here I've got 4 land masses represented by these nodes, and each of the black lines are my bridges. And the question is, now what's the question? The question is, pick a node, can I cross each black line once and only once, and make sure I cross every black line once and only once? And he realized from this, this is impossible. So what he's taken this very high def sort of map and distilled it down to this very low res version of the question, and he's able to answer the question. Can anyone see why it's not possible? So, odd numbers, that's the one. So if you were to cross each bridge once and only once, that would mean each landmass you have to leave as many times as you arrive, which means each vertex should have an even number of edges emanating from it, and they're all odd. So from that, you can immediately see that this is not possible, which in the original representation is maybe not as clear. So how do we take these ideas from topology and bring them into data analysis, which is about, topologies are all about continuous things, surfaces, these kind of things. Data analysis is all about discrete things. Oops, I hit the back button. So how do we take these ideas and bring them into what is essentially the polar opposite world? So the fundamental idea can be summarized this way. We're going to take, so starting with a continuous thing like a circle, if we cover it with sort of from top down, sort of a red bit, some blue bits, and a yellow bit down the bottom, and on the overlap, you can see there's sort of a little bit of purple and a little bit of green, that's blue plus yellow. So then we can represent the red bit with a red node, the blue bits with blue nodes, and the yellow bit with a yellow node. And then wherever they intersected in the overlap, we'll draw an edge. So now what we've done is taken this continuous circle and reduced it down to this very low res circle kind of thing, right? I mean, it's more square, but it's, it has the same sort of topological features as a circle, namely it has a hole in it, right? That's sort of the fundamental shape feature of a circle. So to do this with data, so now we have a discrete set of data. We do the same thing. We bin the data points in sort of, think of it sort of binning from top to bottom, and there's some blue and yellow, and then where they intersect, it's a sort of green, and in the middle, there's some red bits, etc. And then we convert that into this low-res network structure. So the way to think of this is each node here is actually a cluster of data points, and 2 clusters are connected if their clusters interface. Right? So now we have this kind of network representation of a data set. And so this data set, you could imagine I could turn up the resolution here and have, say, 1 billion points. It would still be the same low-res network that represents it, right? And it still had, the network still has the same features as the original data set, namely there's 2 visible holes, right? And that's sort of the important shape feature here. So topological data analysis is exactly, this is sort of one of the fundamental tools in topological data analysis. You divide your data into groups, whatever your data set is. Each group then gets represented by some node, and the relationships between the nodes, so the relationships between the nodes are expressed by an edge connection. So the result is a coordinate-free, right? I don't care so much about where this network is, just that it stays connected in the same way with the 2 holes in it. It is deformation invariant. I'm allowed to stretch it and move it around. That's not what's important. What's important is how the clusters are positioned with respect to each other. And it's a compressed representation because it's now a handful of nodes and a bunch of edges, and that's it. And so what we get from our very high, possibly large or a complex data set, we get this very low res thing that still respects the shape of the original data set. So it captures sort of the large features here, and here is on the right here is such a network. It had like over 1 billion data points. This is some diabetes data. But you can see, so these are some nodes and edges. It's quite hard to see, but this is a network. And you can visibly see there are some distinct shape features. You can see there are a bunch of little loops. There are some flares going off in various directions. There's a big gaping hole in the middle. And the question is, you can already see that you could start asking the question, well, what do each of these bits mean? And what do they correspond to in the original data set? Why is it significant that there are 3 chunks? What do those 3 chunks represent, etc.? So then you could ask, so this is a process we can do to, you could ask, well, what kinds of data sets can we do this process to? It turns out quite a lot of them, right? All you need is a way to tell 2 data points apart in the sense of how far away are they in some kind of distance measure. So it could be Euclidean distance, it could be Jaccard distance, it could be cosine similarity, it could be, there's all kinds of different ways you can measure how data points, and it usually depends on the context of the data, right? But as long as you've got some way to say these 2 points are closer than these 2 points, then you can apply this method. That's literally all it requires. So visually, we have some points. You can visibly see that point A is further away from the rest of the points. Point D and E are close, point B and C are close. So that allows us to build a dissimilarity matrix or a distance matrix, right? So you can see here sort of numerically. And again, because we don't really care about coordinates, I don't really care what these numbers are, I just care about their relative differences. So in fact, I just need this, right? I just need to know, so here it's colored dark if it's small, light if it's large. And you can see I've just got this kind of symmetric heat map of what I need. And from that, from just this alone, I can build such a network, right? So as long as you give me, whatever your data is, you give me a way to measure distance in some way, in some sensible, meaningful way for your data set. And that's usually the most important choice in all of this, right? If you pick the wrong distance, you're going to get some weird phenomena. So there's sort of a bit of an art form here in understanding your data and what is the meaningful distance measurement in the context of that data. So there is some of those. So this is sort of the most meaningful choice you'll make, and the rest is not so important. So just to point out, so what can you do with these low-res sort of topological networks of data? So I'll just point out sort of one big application and then sort of mention some others in passing. And I'll go, if you come back tomorrow night, I'll go into sort of more, more details on these applications. So sort of as a sense, sort of a sense check, like make sure, does this actually give us anything? Can we actually do investigations this way? Or is this, just a madcap idea? We take, there's a classic Netherlands Institute of Cancer Research data set of breast cancer patients. There's 272 breast cancer patients, and their microarray analysis of those patients. So the microarray tests all their gene expressions, like 12,000 different gene expressions. And so I think that in this case, so for this study, I've just taken the top 1,500 genes, because there's otherwise 20,000. So the ones that were expressed most. And so what I end up with is a 272 row, 1,500 column matrix of numbers. So it's not a big data set by any stretch of the imagination, but it is, if we understood this data set, we would understand breast cancer. So it's a complicated data set because there's some hidden things here. And if you do this, I've obviously skipped over some details of how you actually, like I said, you color the network. I never told you exactly how I color the data points. So how I bin the data points is somehow special. But through some playing around, you end up with a network that looks like this. So here's a low res. So this is, there are a lot of points here, 272 different individuals, but I've got this very low res network. And you can already see it has some shape features. It's largely in this weird line, and it has these two sort of arcs. And keep in mind, just remember what this represents. Each node here is a cluster of patients, right? Each edge means those two clusters somehow intersect. They share patients, right? So if there's an edge, it means those two clusters somehow overlap. So you get these distinct shape features, and you can sort of ask, well, what are these two? Why isn't this just a blob? Why is it a line? Why has it got this Y fork at the end? So what you can do is start running through the variables and color the nodes by the average expression of each variable. I've got 1,500 of them, right? So I can run through 1,500 different variables and just color the nodes based on those. Or I could color them by some extra bit of detail, which I didn't use in building this, which was the mortality rate. So some of these patients, unfortunately, didn't survive. They had breast cancer after all. So I could color the nodes by the variable called event death. So if it is red, that's sort of unfortunate. If it is blue, that means they've largely survived on average. So blue is low, red is high. So here we've colored the nodes with an auxiliary variable that we didn't use in the building of this array. And so you can see already that top arc there is almost completely dark blue. They all survived. Whereas down the other fork, at the very tip, you can see it's almost all red. So they all died. And so that's sort of interesting that the shape has actually distinguished between those two groups of patients. I didn't do anything. I just said, I want to group the points together and connect them in this network. But the network itself has separated these two quite distinct groups of people. So all of these people had some kind of tumor, but some of them, 100% survival. And that's represented here in this shape. So you can see here that the shape feature is somehow organized, sort of this variable. And of course, this isn't just automatic. You sort of have to do a bit of hunting, but it's a lot faster than staring at just these numbers and trying to understand it. Because this is such a low-res thing, you can literally just say, okay, let's investigate this. So I can say, there's some features here I want to understand. Why are these all blue? Why are those ones largely red? And there's a sort of a tip at the end there that's quite red too. So now what have I done here? I've selected a bunch of patients, right? A collection of patients. I can compare them. I can run statistical tests of this group of patients, say in group A versus everyone else. So I can do, in mathematics or in statistics, what's known as hypothesis testing, and run through each gene, the 1,500 genes, and say which gene is overexpressing or underexpressing in this group of people, right? And what you find, in fact, so here's a more high-res version of this map, you can find that different bits of this graph, different genes are overexpressed. So running through them now, I don't know anything about breast cancer research. This is just what the data, this is just the titles of the data, the columns of the data that were represented. But you can visibly see that there are certain columns that are overrepresented in those bits. And so you can find out that there are certain aspects, certain parts of your data that are declaring this person's mortality rate will be low. So in this way, just by organizing your data in this topological network and then picking out the shape features and then running tests and saying, what about this feature is significant? And you get back a sort of an ordered list of your columns, basically, or your features that say, well, these 5 things were overrepresented. And now you're already in a much better place than you were when you first started, because you know exactly what columns to look at and focus on. So for those that have seen sort of clustering, classical clustering before, you might ask, well, how does this differ from just clustering? So here is classical single linkage hierarchical clustering of the same data set. And I've put in red the people that died, right? And you can see they are not together. If you do classical clustering, They are not, there's no way you would be able to sort of see that just from classical clustering. So something about so this is ignorant of the shape of the data, right? It's just sort of, so classical single linkage clustering literally just says, start with all the data points and now combine two data points if they're really close, and then consider that one data point, and then connect that with the next thing that's closest to it, and so on, and build it up. And so that's what this sort of level is. If you take a sort of a horizontal swipe, so if I took a horizontal swipe up here, I'd have two clusters. Everything that is, I guess it goes down there, will be in one cluster, etc. So depending on where you do a horizontal cut, that's how many clusters you'll get, depending on how many lines you cross. But as you can see, all the mortality, the high mortality patients are completely dispersed through this. So it doesn't detect the same thing. And just sort of one more sort of example is, here is just sort of an example of sort of some diabetes, the raw data. It's just, these are taken from a blood titer, where they just basically measure various quantities in your blood, glucose levels, et cetera, They're not actually testing for diabetes. And then there's an auxiliary variable on whether they had diabetes or whether they had type 1 or type 2, which was not used in the building of this thing. So this is the network you get. You can see already there's some chunky sort of flare down the bottom here, and then two flares out the side. And if you do this same analysis, circle each flare one at a time and ask the data what's significant about this piece, run the statistical tests, get the ordered list of variables and ask what's the driver, it turns out that the big chunky bit are the normal patients. People didn't have diabetes. One of the flares was type 1 diabetes, meaning you're essentially born with it, and the other one was later onset type 2 diabetes. So the shape of the data actually told us exactly where you sit on the diabetic spectrum. So if a new data point comes in, I can see wherever it lands, I can tell you, without testing for diabetes, I could tell you which one of these three you are. Right, so that gives you, this is what I mean by understanding the shape of the data allows you to derive significant value just from knowing that shape. And again, this was a very large, sort of millions of patients data set, but this graph here is quite easy to digest. But keep in mind, oh, and I should have mentioned that these are sized based on the size of the node is the size of the number of patients in that node. So the bigger nodes, the chunkier nodes down there, means there's a lot more patients in that normal spectrum. And so there's a lot more people up in that tip of type 2 than there is down in type 1. So just briefly to sort of round out some other sort of applications that you can do with this. So those are some quite serious ones, but really the main principle is that this process of building this topological network from your data set allows you to give you an unsupervised way to self-organize your data, right? You don't have to, you don't make the choices. The choice is determined by the shape of your data. Like you don't have that choice, and the shape is significant. So this allows you to do things like find weak signals in noisy data, because the weak signal will come out as a shape feature, right? It's, as I said, if it's not random data, it will have a structure, and that structure will present as a shape. And so you can use this to do things like, if you build a machine learner classifier or a regressor or something, and you find out you get 82% accuracy, you might want to say, well, why can't I get more? So another way to phrase that question is where, like literally where in my data is failing? Like, can I see it? Can I see there's a chunk of bits? Or maybe it's multiple chunks, right? Maybe there's lots of little bits, and you could ask, okay, what's significant about each of these chunks, and investigate them and realize, that's failing for this reason, that's failing for some other reason, and then build up an ensemble method sort of a combination of like a patchwork quilt of learners. So the advantage of this approach, first of all, it's very efficient. The process I outlined is like highly parallelized, and so you can handle sort of billions of data points in, you know, seconds or minutes, depending on the data set. And it gives you this sort of universal approach to simultaneously searching or querying your data, but also segmenting your data into interesting pieces. And so using this, you can actually build up ways to accelerate accuracy, reduce training times, and even reduce the amount of training data you need to train things like machine learning algorithms in general. So for those that know about things like convolutional neural nets, these things are about understanding images, and the way it treats an image is as a grid. But that's a property of images, right? That is a shape feature of images. They are represented as grids. So if you wanted to apply a convolutional neural net to a different data set, probably a grid is not the shape of the data you're trying to put on it. So what you should do is find what shape it is, and that should be your initial shape. And then you can go through the whole process. And what you find is you can use a lot less data, accelerate your training times, and get improved accuracy because you're embedding the shape of your data into your convolutional neural net rather than just saying, I'm going to pretend it's an image, which for a lot of the time is just not the case. So that's sort of all I wanted to say. I wasn't aware I could have just given a 5-minute lightning talk. So if I had been told that, I would have been even faster. But I'll just leave you with this prototype we're working on in Visio, which is the part of Brandwatch I work with, which is to do with visual analytics and representing live data. So this is a topological network of some mentioned data, and this allows you to sort of select pieces and do this kind of same investigation on text, sort of social media data, and understand what are the driving forces. So if you want to think of that, oh, no, that wasn't quite done. And so you can work out, so what that's doing is taking a bunch of mentioned data online of conversations about a particular query that I've made and clustering it. So what you can actually see there is those different colors are effectively conversations around a topic, right? So I could pick, say, Nike shoes, and you could have one conversation about MX1s or another conversation about high tops or etc. Or people burning Nikes because, I don't know, their manufacturing processes. But they would be represented as different communities in that network.
Sorry, I'm trying to get it back.
Yeah, there's just one last slide. But I guess the last slide was just for questions anyway, so any questions?
Yeah.